Okay, so today I'm going to talk about the finite element analysis approach that we discussed last time. And so when we finished last time, we were kind of in the middle of a calculation. And so we were trying to solve this weighted residual 2D problem where we've got the weighting function, derivative of the weighting function with respect to x, the derivative of the magnetic vector potential with respect to x, and this magnetic vector potential is a trial function. So this is the trial function for a single triangle which has the three nodes AI, AJ, and AK. So this whole problem is trying to solve the field within one triangle. So we've got this trial function here that we wrote out previously. And so then we could take the derivative of the trial function with respect to x, and then we also took the derivative of the weighting function, which was made equal to the basis function. These are these n terms of the basis function. They're also called shape functions in your textbook. So we made the weighting function equal to the basis functions. And then we obtained this matrix here, equation 30, and we did the same thing for the second term, and we obtained the equation 31. So now we can put these into the first term of 26. But we've still got a double integral here. However, if you recall from the previous lectures, the QIs and the RIs are simply coordinate positions of the three points here. And so they are not functions of x or y, they're just positions, so they're just numbers. So because of that, then there is nothing inside of here that is a function of x or y. So then we finished last time by noting that we could take the terms in here outside because they're not functions of x or y, and then we're left with just the double integral of 1 over the area of the triangle. And so that will then give us this will then give us the triangle area, which I've called delta. So then we have the complete solution for this first integral term. So let me write that out. So we just add these two terms together, and then we multiply by delta because of the integration of the area to delta. So if we substitute, this is equation 33 here. So substitute 30, 31, and 33 into 26 gives 1 over 4 mu delta. So one of the deltas cancels out. And then we have qi squared plus ri squared, qj, qi plus rj, ri, qk, qi plus rk, I, and then the second term is qi, qj plus ri, rj, and then qj squared plus rj squared, and then qj, qk plus rj, rk, and then qi qk plus ri rk qj qk plus rj rk, and then qk squared plus rk squared, and then that's all multiplied by ai, aj, ak. Okay, so that's the first term in 26, but we still have the second term, so that's plus, oh well, I guess I'll put it as minus, and I'm going to take the current out of the integral. I'm going to assume that the current is the same value with inside the triangle, but we still have this weighting function term in here, so that has to equal 0. Okay, now that's obviously a lot of writing out, so we could reduce this down and write it succinctly. SII, SIJ, SIK, SJI, SJJ, SJK, SKI, SKJ, SKK, and then that's times AI, AJ, AK, plus J naught. And now the weighting function, remember, was equal to the basis function, which is these n terms. Now in matrix form we said that previously we wrote that out as Ni, Nj, Nk, like that. So this is the weighting function for the three terms. So this is actually, so this first matrix here, so this first matrix, this matrix here has a special name called the stiffness matrix. Because that comes from mechanical analysis, because mechanical engineers did this stuff before electricals. So due to FEA development from mechanical analysis, the coefficients, the coefficient matrix, and I can call that just S. Actually, I'll put a square bracket around it. The coefficient matrix S is called the stiffness matrix. Okay, so now the last part that we have to figure out though is this bit here, and I could just write out the solution, but I think it's I should explain where it comes from. So we've got these three weighting terms here, which are the basis function terms. So let's rewrite these, and let's evaluate what this is. So we can substitute in the terms from previously. So substitute 19 to 21, that's where we defined Ni, Nj and Nk, into second term in 35. 35 was the one I just erased here. This is 35 here. Gives, so we've got J naught over 2 delta. Now we've got the double integral pi plus qix plus riy pj plus qjx plus rjy pk plus qkx plus rky, and that's dx dy. So this is 36. So this is what we need to figure out. And now we can use a concept called the theory of centroids to work out what this integral is. So let me just review that briefly. So this integral can be calculated by utilizing the theory of centroids. So what that says is that if you have a function, so the average of function f on an area omega is going to be equal to going to be equal to 1 over the area of omega times the integration of the function, in this case 2D, over that area. So let's think about what this means in 1D. Let me write this out and then I'll explain further. The centroid for a plane region omega is the point x, y, where x is the average x coordinate point, and y is the average y coordinate point in the region omega. So for example then, if you have, so if you think about the distribution in 1D, if you had some material that this is some material here, the 1D, it's got only one dimension, but the material is spread across there uniformly, then the location x hat is the average position of that material, and that would be at the center where it balances with gravity. So if you had equal weight on here, it would balance. That's what that's what this is saying. So we can calculate that, for example, in 1D or 2D using this concept. So in this picture here, the average of x would be equal to 1 over the area omega, where we integrate x dx dy. And then, so we'd evaluate the x over this area, and then y is equal to 1 over the area of the material, for example, times the integral of y dx dy. Okay, so with this definition, then, if we think about now our triangle, then the centroid would be at some point in the middle where it balances. If you could imagine it sitting on, if you try to balance the triangle, and it was a uniform distribution. So then that's the centroid point. So we're going to use that concept so that we can replace the x and y in here by the average x and y, and then we won't have to. Then the trick is then that we won't have to do any integration, because we'll replace this x and y by an average value. Take it, and then we'll be able to take it out. It's a bit of a trick. So if we so for this case here, so for our case, we may write that x hat is equal to xi plus xj plus xk divided by 3, and I'll call that 37, and y, the centroid point for y is yi plus yj plus yk over 3. So you're kind of averaging it. So average position in x and y direction. Okay, so now if we look at these definitions here, we can, for integration over a surface area, this is a integration over a surface area here, and so so this area delta, this area for our triangle problem is defined as delta. So then, if we take this equation, these two equations, and we multiply by both sides by, for the first one, if we multiply both sides by qi, we will get it in a similar form. So let's do that. So multiply. So let's take these two and rewrite as. So if I take both of them, and if the first one I multiply by qi delta x hat, okay? So this here we can put as delta here. So I'm multiplying the left side by qi delta. And then on the right side I'll multiply that by qi delta. And so then we end up with the double integral of qi x dx dy, right, like that. Now that's this is an average value, some number, and qi was defined earlier. It's got the coordinate positions in it. Delta is the area. We could, if we wanted, then we could rewrite the delta as an integral like that. So now, because delta, remember that delta is equal to the double integral of 1 dx dy over the area, right? But remember, this is evaluated over the area of the triangle. So this is equal to the area of the triangle. So qi is just some number. X is the average of the x positions, and multiply by delta. But we could replace the delta with the double integral. So now we have on the left side qi times the average of x is equal to qi times x on the right side. And then we can do this same thing for y. So we can multiply the left and right side of y by ri. I want to multiply by ri because there's an ri here. So we have the final result is really simple, but getting there is complicated. So we multiply the left and right side of this second equation here by ri and delta. So we have ri delta y, and that's going to be equal to the double integral of y dx dy. And then since this again is delta, we can rewrite this left side as the double integral of ri y average dx dy. Okay. Okay. So now we've got the relationship between y, which is something we have to integrate a variable. Now we've put the average in, and so we don't have to integrate this term here. But the reason I wrote it in an integral form is to allow us to substitute everything back into the matrix equation. Okay. Actually, I say okay too much as well. Now see now I want to say so, but I say so too much as well. What's another word for instead of so and not okay? I'll just be silent then. I need to say it. Okay, so now, there we go. Now I feel better. Okay, so now we're going to, let's look at this first term here, right? So let's, just the first term. So we've got J naught over 2 delta, and then we've got this double integral pi plus qix plus ri y dx dy, right? So this is I'm going to give this a name, and I'm going to call it equation 42. No, I'm not. I'm going to call it 41. And then this was this is. You're okay with this? This top one is equal to this one here. Is that okay? You see that? So this is equation 39, and then this here is equation 40. Okay, so if we look at equation 39 and equation 40, and then we look at equation 41, we can see that these first two terms are in the same form. So now we can, and pi is not a function of x and y, so we can substitute 39 and 40 into 41. So 39, 40 into 41 gives, so we have J naught over 2 delta double integral pi plus qi x hat plus ri y hat dx dy. Okay, now these two are the average pi is not a function of x and y, so we can take out the dx dy. So then so that allows us to simplify it down, but we need to rather than doing that right now, I'm going to because there's more to it than that, because we still have to we still should look at substituting all of these back in here and seeing what we get. So I'm going to leave the integral there for now, and I'm going to now substitute in the pi, the qi, the x hat, the ri, and the y hat, and see where that takes us. So so substitute 37 and 38. That's these two, and pi, qi, ri. If we substitute all those into here, let's see what we get. So we've got J naught over 2 delta, and now expanding out. So we defined these earlier. This was a simplified notation for the position information. So the pi is equal to xj yk minus xk yj plus the qi is defined as yj minus yk. You'll have to look back in your notes for the definitions of the pi, qi, and ri. I've just taken them off my notes, but I did check this again before the lecture. Xi plus xj plus xk over 3, and then we've got the third term, which is xk minus xj times yi plus yj plus yk over 3, and that's dx dy. So then we can multiply both sides by, we can multiply everything by 3, so we get j naught divided by 6 delta, and then we can integrate. Then we've got all these terms inside of this integral here. So we can, if we look back at the definition for the area of a triangle, if you rearrange this here, all of these terms, and you look at the definition of the area of a triangle, which is I get you to check that for problem 1 of the homework 2, then you can rearrange this and see that you get out 2 delta. So this reduces down to j naught 2 delta. That's the term. That's the term inside of this brackets, and then we're also, so that the part inside of the brackets is equal to 2 delta, but there's no x and y in there. It's just parameter information. So if we take, so we can rewrite this as dx dy 2 delta, and then we'll get 2 delta squared, like that out of here, and that, but we have j naught over 6 delta here. So we get, let me write that here, so we get j naught 6 delta, this integral becomes delta, and the part inside of the integral hasn't got any xy terms, but it's the equation for the area of a triangle, twice the area of a triangle, which you can check, and so then we get a 2 delta here squared, because this is delta here. So that simplifies down to j naught delta over 3. That's what we're trying to get. So I skipped the writing this out, but if you write this out, a few terms cancel, and then you can see that it's the equation for 2 times the area of a triangle. So with this result, then that gives us the evaluation of the first term here, which is the first term in this matrix. So with that information, we can then write that this whole thing here is equal to, so you can do the same procedure for the second one, the other 2, if you don't believe me, you can check the other 2, but you'll get the same result. So we end up with the current, times the area of the triangle divided by 3. So this is equation 44, and this is 43. Okay, so now we've got the second term. So we can now write out the complete solution of equation 26. So 44 back into, sorry, 30, well, I wrote out 35. Yeah, 35. So 40, this is 44, back into 35 gives 1 over 4 mu times the area, and then we've got the stiffness matrix. Plus the source, which is now this here. So what is current density times area? What's that going to be? So note what does the current density times the area equal? So if we have a triangle and we say that within that triangle region it has a certain current density, if you multiply that current density by the area of triangle, what would it equal? Current. So that's the current. So this is the current going through that single triangle. Note equals the current passing through triangle under consideration. So if you have a problem, electromagnetics problem, and you divide up your problem region, you need to keep in mind that the FEA program will be defining the current over that whole triangle as being a uniform value. So that's important, especially if we then include, we're just doing static, this is just static, but if we had time varying as well and you had eddy currents, that's very important that you make sure that the conductivity of that the triangles are small enough to account for eddy current effects and things like that. So it's important to recognize that the current is going to be the averaged value over that whole triangle. It's just going to be one known value.